Hi everyone, my name is Yifeng. Currently, I am a second-year PhD student at Purdue University. I'm excited to present our paper, Software Entity Recognition with Noise-Robust Learning today. This work was done in collaboration with Tai Ren, Johan Li, Professor Muhao Chen, and my advisor, Professor Tianyi Zhang. Software entity recognition is an essential task for acquiring software-related knowledge. Here is a sentence from PyTorch API documentation. The task of SER is to identify and classify software engineering related objects in text into predefined types. Software entity recognition is the backbone of many downstream software engineering applications. For example, traceability link recovery, automated documentation, API recommendation, and bug fixing. SER has evolved from pattern matching to machine learning to deep learning. Deep learning models are the leading paradigms for named entity recognition in general text and can also be adapted to recognize software entities. Recently, SoftNER has been proposed to detect fine-grained software entity types with a model fine-tuned on Stack Overflow data. However, existing SER approaches, including SoftNER, have two key limitations. First, domain shift, limited vocabularies, and morphological names in software engineering limit coverage of software entities in real text. For example, the SoftNER dataset only covers around 7,500 entities. Second, noisy training data hinders accurate SER. Manual analysis of two existing SER datasets find that the SNER dataset has a labeling error of about 14%, and the SoftNER dataset has a labeling error of about 18%. To address these challenges, we propose our approach in two ways. First, we leverage Wikipedia to build an automated pipeline that develops a large, high-quality software entity dataset called Wikiser. Second, we propose self-regularization, a noise-robust learning approach that accounts for noisy labels in our Wikipedia dataset. Let's first look at the Wikiser construction pipeline. It has three steps. The first is to extract SE-related wiki categories. The second is to extract SE-related wiki articles. And the third is to type recognized entities. In step 1, we peruse the Wikipedia category taxonomy to extract all SE-related subcategories under the computing category. This picture shows the direct subcategories under the computing category. We manually peruse them to remove non-SE-related subcategories. We get about 7,500 SE-related categories after step 1. In step 2, we extract wiki articles under the SE-related categories, filtering out non-SE-related articles such as software studies, which is shown in this picture. It does not refer to a specific software entity. We manually sample 385 articles to decide filtering rules and extract 80,000 SE-related articles after filtering. Then we extract the sentences in these articles and use hyperlinks on Wikipedia to identify entity mentions. For example, here is a paragraph from the Kotlin Wikipedia article. Hyperlinks to SE-related articles are captured for further processing. We also leverage Wikipedia page redirect mechanism to detect aliases to a software entity. For example, the Wikipedia article for named entity recognition has 14 redirects. We treat the titles of these redirects as aliases for named entity recognition. After step 2, we have 3.4 million sentences in total and 1.7 million sentences with software entities. In step 3, we need to infer the types of these software entities. To achieve this, we define 12 fine-grained software entity types, which are listed in this table. For example, bubble sort is an algorithm and Java is a programming language. We manually label 1,160 categories from the root category. automatically propagate labels to remaining categories using the hierarchy, and establish a mapping between 7,524 categories and 12 entity types. We infer entity types from categories by designing heuristics, and most types match their most fine-grained parent category, such as categorizing Kotlin as a programming language, since most of its parent categories, which are shown here, are labeled as programming languages. Here is a comparison of our dataset to the existing SER datasets. Note that the soft NER dataset contains 20 entity types, and 8 of them are trivial types, such as variable, value, HTML, XML tag, which are not of our interest. Compared to the SNER and soft NER dataset, we have significantly more labeled sentences and unique entities. Manual validation of 385 sampled sentences shows our Wikisr dataset has a labeling error of about 9%, which is much lower than theirs. Although Wikisr has a lower labeling error rate compared with other benchmarks, it is not free of labeling errors. Thus, we propose a noise-robust learning approach called self-regularization. Here is the overview of our framework. It is motivated by the more delayed learning curve of neural models on noisy data than on clean data. Model prediction is likely to be consistent with the clean labels, while it's often inconsistent or oscillates on noisy labels over different training epochs. As a result, labels that are different from the model's predictions in the later epochs of training are likely to be noisy and should be downweighted or rectified. Self-regularization uses prediction agreement of multiple models during training to achieve this and prevent the model from overfitting on certain noisy labels. Concretely, this is the algorithm of self-regularization. We first initialize a model M, from a pre-trained language model such as BirdBase. The first 10% training steps undergo a warm-up phase. Then, at each training step, a random batch is sampled and forwarded multiple times with dropout to obtain probability distributions, which are likely to have high variance in noisy settings. Therefore, after computing task loss by equation 2, we compute KL divergence loss by equation 1, hoping to control for such variance. Finally, the combined agreement loss is computed by equation 3, and the model parameters are updated. We did multiple experiments to evaluate our approach. Since the original Wikisr dataset is too large to train on our GPU machine, we create a smaller dataset called Wikisr Small to train and test SER models. We also compare our approach to multiple baselines, including soft NER, co-regularization, BirdBase, RobertaBase, BirdOverflow, and BirdLarge. On our dataset, self-regularization improves BirdBase F1 score by 3.2% over vanilla training. It also outperforms recent approaches such as soft NER by 7.1% F1 and co-regularization by 2.9% F1. Overall, our approach achieves the best performance, and the performance improvement is generalizable to larger models. On two existing Stack Overflow datasets, self-regularization is also generalizable. The table shows that the positive gains from self-regularization also apply to soft NER and SNER. BirdOverflow trained with self-regularization performs the best on both datasets. To conclude, this paper presents Wikisr, a large, high-quality SER dataset constructed from Wikipedia, and self-regularization, an effective noise-robust learning approach. Together, they advance state-of-the-art software entity recognition, achieving improved performance over multiple baselines on Wikipedia and Stack Overflow benchmarks. That's the end of my presentation. You can find our dataset, source code, and models on GitHub and Hugging Face. Thank you very much.